So now we've been introduced to the fundamental trigonometric identities. We can expand upon our list of identities and formulas in trigonometry, moving now into the addition and subtraction formulas, which can also be called sum and difference formulas for trigonometric functions. Here we have them defined for the sine, cosine, and tangent. And by fundamental identities, we could also define similar ones for cosecant, secant, and cotangent by using, for instance, reciprocals. So these are the primary three. And really, we could say we really only need to know the sine and the cosine formulas, because the tangent formulas, as we'll see when we can prove these formulas here for tangent, they can be proven by starting with the use of a sine and a cosine as a ratio. We'll take a look at least one of those, the tangent formulas, how to do that. All right, let's take a look back at the fundamental identities we've already seen so far. We have the reciprocal identities, where the three reciprocal trigonometric functions are defined with respect to the original three trigonometric functions, right? So the reciprocal of sine, reciprocal of cosine, and the reciprocal of tangent, right, give us the three reciprocal trigonometric functions. Now we can refer to the tangent and cotangent as reciprocals of each other. Okay, I like to think of these, though, instead as ratio identities right here. That is, that the tangent, for example, is the ratio of sine to cosine, and the cotangent is the ratio of cosine to sine. So we've already proven these identities. So these are accessible to us now to use in future proofs and in formulas for evaluations, for instance. We already know that these are true because we've proven them to be true. The first three, the proof is really by definition. They were specifically defined this way. The tangent and the cotangent, though, we're able to prove the tangent. First, we could prove it with a right triangle trigonometry, for instance, and then we could prove it also with the definition of the trigonometric functions in the coordinate plane. The Pythagorean identities are proven initially using the equation of the unit circle. The unit circle has the equation x squared plus y squared is equal to 1, and for any terminal point in the unit circle with coordinates x, y, the sine of x, well, the sine function would be the y coordinate, and the cosine function would be the x coordinate. And the equation of the unit circle, of course, is that x squared plus y squared is equal to 1. Now, this could create a bit of confusion here that we're saying that x is equal to a cosine of something, but in this formula we have the cosine of x. It's really just a matter of choosing a variable for the input, and that's all. So, for instance, over here, if we say, well, in the unit circle, if x equals the cosine of t, and y is equal to the sine of t, and that's by definition of the trigonometric functions itself, then plugging those into the formula for the unit circle, we would get cosine squared t plus sine squared t is equal to 1. And then replacing t with some other input variable, whether it be theta or u or x or any other variable we want, we would still have this identity as true, regardless of what the input variable is. It's more important when looking at a variable to consider what is it representing. Here, the input variable t is thought of as the distance along the unit circle. If we used theta, we would think of an angle of rotation, or measure of a rotation. Here, x is just standing for whatever the input happens to be, whether that input is an arc length or an angle is irrelevant, whatever the input happens to be. But what is important here is that this input and this input are the same as each other, right? They're the same value being input. We are summing the squares of the sine and the cosine, which comes directly from the unit circle formula, which comes directly from the Pythagorean theorem, right? For any point on the unit circle, no matter in which quadrant it falls, we can, in general, construct a right triangle, and that right triangle would have to satisfy the equation x squared plus y squared is equal to 1 squared, because the radius of the unit circle is, of course, 1. Now we can use the reciprocal identities and ratio identities in order to derive the other two Pythagorean identities. For instance, divide everything by cosine squared, you would get tangent squared plus 1 is equal to secant squared. And if you divided everything here by sine squared, right? Divide this, this, and this all by sine squared of x. You would get 1 plus cotangent squared is equal to cosecant squared. So you would just derive these identities from the initial identity. Generally speaking, the first identity in a bunch is the most challenging one to prove, and we usually go to some geometric interpretation and use of the definitions and previous identities in order to prove the first of the batch. Then usually once we have one of them proven, okay, we can use previous identities in order to prove the other ones as well. That's a strategy we're going to use here as well in this section when we're proving the sum and difference or the addition and subtraction formulas. The even and odd identities, those can be, one way to prove those would be by using the graphs of the functions. For instance, the graph of the sine of x and the graph of the sine of negative x. Right? And the graph of negative sine x, for example. Now, we can also use the definition of even symbolically is that f of negative x is equal to f of x, okay? And the geometric, okay, the geometric interpretation of that would be that we have for any point on the curve, okay, for any point on the function that would satisfy this condition, okay, that's where the y coordinate is f of x. I can write that up here, right? This y coordinate is f of x. Then we're going to have a reflection over the y-axis of that point. And so that would be located at, that would be located at negative x, y, right? Because if we have x on this side, then we would have the opposite of x on this side, right? So any function that geometrically satisfies that for any point you choose on the function, that it shows up by reflection on the other side of the y-axis as well, right? So if every point is paired with a point on the other side of the y-axis, with the only exception of being if there was a point on the y-axis itself, then it would be its own reflection, okay? But otherwise, any graph that satisfies this kind of symmetry is automatically an even function and would have to satisfy this type of symbolic relationship. Cosine is an example of a function that does that. The cosine graph, y equals cosine of x, looks like this. All right. That is that if we choose any point that we want off of the y-axis, if we choose any point that we want, that point is going to have a reflection of itself on the other side of the y-axis. This would be true for every point we choose. So this, therefore, cosine is an even function. So it satisfies that f of negative x is equal to f of x. The sine function satisfies that it has the odd symmetry. Odd symmetry symbolically can be written as f of negative x is equal to negative f of x, which we can interpret as saying that if you switch the x value to its opposite sign, then the y value would also switch to its opposite sign, and we would see a reflection. So if I have a point with coordinates x, y, like for instance here, if I'm in quadrant 1, then x and y are both positive. Okay, if we switch x to negative and y to negative, we would be talking about a point here in quadrant 3. Any function that satisfies this kind of symmetry, okay, this kind of symmetry whereby you can see by a double reflection, let's say a reflect up this way and then reflect over that way, and we would see an image of itself. Okay. That double reflection indicates an odd symmetry. It's also thought of as symmetric about the origin. You can also represent this through a rotation. It doesn't have to be a double reflection, but it's the same as doing a rotation by 180 degrees. It would overlap itself. Now the sine function, okay, the graph of the sine function, all right, we have a wave that looks like this, and then it continues on from there. But if we continue it to the left of the y-axis, it looks like this. Notice now that if we were to take this whole wave and if we were to rotate it about a pivot at the origin, rotate it by 180 degrees, it would overlap with itself. Okay, just as like if we were to choose a point up here in this quadrant, okay, if this is where x is negative but y is positive, if we would switch the signs, that is to make x become positive and y become negative, we would see another point in this quadrant down here. That satisfies odd symmetry. So the sine function is odd, and the tangent function is also going to be odd. Okay. One way to show that geometrically is by looking at the graph of the tangent function. It's like waves like so. If you were to rotate this by 180 degrees, it would overlap itself. And the other way to see that that's so, that the tangent is in fact odd, is to use fundamental identities. Tangent of negative x would equal the sine of negative x over the cosine of negative x. That's known because tangent equals sine over cosine of the same argument. And we've already demonstrated that the sine is odd. That is, we know that the sine of negative x is negative sine of x. And the cosine of negative x is equal to cosine of x because cosine has already been shown to be even. So this equals cosine of x. Well, then we have negative, a single negative here, and then we have sine x over cosine x. Well, that would be tangent of x. So we've just shown that here now, without using a graph, okay, here by using identities we have already established, we've shown that the tangent of negative x is equal to negative tangent of x. Therefore, we have proven, okay, that tangent of x, okay, is in fact odd, okay, that it has odd symmetry. Okay, so this is proof, all right, that the graph would have to have that kind of symmetry. Okay, so again, usually the most work is spent on proving maybe the first of the identities in a bunch, and then you can prove the other ones in there by usually using previously known identities. The cofunction identities can be proven geometrically. We can think of the sine of pi over 2 minus u is equal to cosine of u. One way to look at that is to say that this is like a horizontal shift of the graph of the sine of u, for example. And, if we look at the sine curve, here's a sine curve right here, a standard sine of x curve. If this were shifted to the left by pi over 2, that would move the maximum point to the y-axis, right? If we shifted this by pi over 2 to the left. But that would exactly then overlap with what the cosine function is. Vice versa, if we took the cosine graph and shifted it to the right by pi over 2, we would exactly get the sine function. So this is really explaining symbolically that in fact what we have is that the sine and the cosine are horizontal shifts of each other by pi over 2 as long as it's in the appropriate direction. We'll take another look at these identities here in this section because these will allow us to utilize the difference formulas. For instance, we'll be able to prove this one here symbolically by using the sign of a difference, the sign of a minus b, or the sign of s minus t, or the sign of x minus y, whichever one of those difference formulas we want. And let's start taking a look at those addition and subtraction formulas now, or they can be called sum and difference formulas, whatever you wish. So I'm talking about this one. I was just talking about this one right here. We can use like a sign of s minus t formula in order to prove the sine of pi over 2 minus u is equal to cosine of u, because pi over 2 minus u would be a difference. It would be an s minus t combination. But we can't use the formula, technically we can't use this formula until we prove that it is actually true. We can't prove that it's true by just plugging in a couple of numbers. That doesn't prove that that an identity is in fact an identity. And these are all identities here. Recall that in order to prove an identity to be true requires that we keep the input variables to be flexible. They have to be allowed to be any number and all numbers within the domain, all simultaneously. If we were to pick specific numbers and plug them in, that is only a technique that can prove a formula to be false. The way to prove that it's true is to not plug in any numbers and show that the left-hand side and the right-hand side would simplify to the same expressions. So where do we start amongst all this? We're going to do the most amount of work here in proving the first one of these, and then the other ones will be a little less work from there. Okay, we're going to start with this one. Okay, so I'll label this number 1 right here. The cosine of a sum formula. Okay, the cosine of a sum, or the cosine addition formula. Prove that the cosine of s plus t is equal to the cosine of s times the cosine of t minus the sine of s times the sine of t. Now the proof for that comes from geometry. How are these things defined? Okay, specifically within the unit circle, how have we defined the cosine and the sine function for different arguments, s and t? Well, here's an image right here that shows how we can set this up. we can consider the input of every cosine function, again, as either an arc length on the unit circle or a central angle of rotation. Let's consider S and T to be arc lengths right now for this proof. Arc lengths. So, if S is a length, a distance along the circular arc in the unit circle, and if T is also a distance that is not necessarily the same distance as S, okay, also along the unit circle, okay, well then, for instance, we could position, let's say we put T is right here, so T is this distance in standard position, and then S, we can put S, we can have S start where T ends, so that we end up getting a total arc length here, right, that would have to equal S plus T. So I hope that makes sense. All right, this is the unit circle we're looking at here. Okay, so the radius is equal to 1. So in that case, then we can define the trigonometric functions, or use the definitions of the trigonometric functions within the unit circle. For example, what is Q1? Q1 is the name of this point right here. Okay, what are the coordinates of Q1? All right, Q1. The x coordinate at Q1 would be the cosine of the distance to get to there. All right, I'm gonna put this distance in green. All right, so that distance in green is t. So the coordinates of Q1, by our definitions of the trigonometric functions in this manner, okay, we would have the x-coordinate is the cosine of t, and the y-coordinate would be the sine of t. That is just by the definitions, again, of the trigonometric functions. Okay, so that would be coordinates for Q1. Now, P naught, well, that's pretty easy right there, right? We can see that P naught, right, is the initial point with coordinates 1, 0. That's for sure. Okay, now we went a distance of s beyond t so that we could go a total distance of s plus t. Why did we do that? Because we are trying to determine something about the cosine of s plus t. So we need to establish what is s plus t as an arc length. Well, this is s plus t as an arc length right here. And so therefore the coordinates of P1, which right here are shown to be in quadrant 2, and it doesn't have to be quadrant 2. This is just an example. It could be in any quadrant. Okay, but it is found from the sum of the distances s and t. What would have to be the coordinates of P1 by the definitions of the trigonometric functions? Well, the x-coordinate would be the cosine of the arc length that it took to get there in standard position. That arc length is s plus t. So the coordinate, the x-coordinate of P1 is cosine of s plus t. And the y-coordinate at P1 would be sine of s plus t. Okay, so we have these 3 points now defined. Now what's with this point down here and why do we use it? Well, we'll notice, okay, now if we were to go from standard position, if we were to go through an arc length negative s, that is if we were to go then clockwise a distance of s, so this is s right here, okay, so maybe this one can be in orange for right now, okay, so that, okay, alright, so that geometrically represents negative s. Okay. Well, then notice this arc right here. Let's choose another color here. How about this purple? Okay. The arc then from Q1 to Q0, between here to here, right? What is that distance going to be? Okay, that is, right, from here to here. What does that distance have to be? Well, this is length t, and this has length s. So this distance also has to be s plus t. So this is the same arc length, this purple one, as this one was right here. Now, when the arc lengths are equal to each other in a circle, geometrically then, the chord, it's called a chord right here, that connects the 2 points, okay, that connects the 2 points that are subtended by that arc length, those have to be equal as well. All right, so this length here from P0 to P1 must be the same as this length right here from Q0 to Q1. They have to be the same because they are both subtended by an arc length that is exactly the same size as well. Okay. So we can then talk about the distances, the lengths of these two sides. Okay, we want, for instance, let's say D1, okay, is going to be the distance, let's say, from P0 to P1. So if I'm saying this is D1 right here, and then D2, I'll call D2 this distance right here, Q0 to Q1. Geometrically, D1 and D2 have to equal each other. Those two lengths of those line segments must be equal. So we want to find this straight line distance. And how do we find straight line distance between 2 points with coordinates x and y? We use the distance formula, which is based off the Pythagorean theorem. So we need to have the coordinates then, the x and y coordinates now for Q0. Okay, Q0. So Q0 has coordinates what? Well, the x coordinate on the unit circle is always found by taking a cosine, and it's the cosine of of the argument or the arc length that it took to get there. And the arc length in this case to get to Q0 in standard position was negative s. So Q0 has x coordinate cosine of negative s. And the y coordinate of Q0 is going to be the sine of negative s. Now notice, by symmetry, that is even and odd symmetry, we can simplify these, so we can choose to write these as well in another form. Like, for instance, cosine of negative s, that's the same as the cosine of s, because cosine is an even function. And the sine of negative s, that's the same as negative sine of s. That's because sine is an odd function. All right, so this is true, okay, because cosine is even, and this is true because sine is odd. It's just another way that we can write the coordinates for Q0 here. All right? And again, if you're concerned, this is the most work that we have to do, is proving this first one. The proofs of these other ones is not going to be as detailed because we're going to be able to use the results of this formula in order to establish what the others look like. Okay, what the proofs of the others would look like. Okay, now let's go with this D1 is equal to D2. Okay, what is D1 formulaically? D1 is going to be found as the square root, right, because we're using the distance formula here. The distance formula, recall, is the, should I write down the standard distance formula maybe so we know what we're talking about? The distance formula between 2 points, okay, would be the difference in their x coordinates squared plus the difference in their y coordinates squared, and then the square root of that whole expression. That's the distance formula. Right? So D1, for example, then, from here, would be, well, that's the distance from P0 to P1. What are the coordinates? Okay, the coordinates for P0 and P1 would be these two right here. Okay, so in either order. So I'll take from P1, I'll take this to be the x1 and this to be the y1 and this to be x2 and y2, for example. So we have the cosine of s plus t minus 1 squared. That would be an x2 minus x1 quantity squared, plus the sine of s plus t minus 0 squared, and that would be a y2 minus y1. Okay, so there's that. That's D1. Maybe I want to clean that up just a little bit. I don't want to expand this, actually. Okay, so we'll see why in a moment. But I want to leave this like this. But over here, we don't have to write minus 0 because we know anything minus 0 is just equal to itself. So I'm going to do plus the sine squared of s plus t. So it's cleaned up just a little bit. And that would be D1. Okay? So that is a way for us to figure out what is the straight line distance between P0 and P1 for any s and t that could have been selected. Now let's find out what D2 is. So D2 is going to be the distance from Q1 to Q0, or the other way around. Okay, So we have the cosine t sine of t on one hand. We have a cosine s and a negative sine s on the other hand. So let's figure out what d2 is then by the distance formula. We have a square root of, now we'll take the difference in the x values first. That would be cosine s minus cosine t, and then that quantity is squared. Cosine s minus cosine t quantity squared, plus, now we need the difference in the y coordinates. That would be negative sine of s minus sine of t. All right. Negative sine of s minus sine of t, and then that quantity is squared. Now we can clean this up maybe a little bit. Okay, so I'm not going to expand in here. I just want to clean this up a little bit. This is going to be cosine s minus cosine t quantity squared. I'll leave that alone. But over here, notice we can actually factor out a negative 1 in this case. Okay, so I can write, because both of these terms have a negative 1, we can take the negative 1 times, this would be sine of s plus sine of t, and then that whole quantity would be squared. All right, so I haven't removed the negative 1 from the square. Still, everything in here is being squared. I've just said that there's a common factor of negative 1 here so far. And then that gets squared, which in other words would just turn this into a positive. Okay, so I have cosine s minus cosine t squared plus sine of s plus the sine of t squared. So that's how that's going to simplify. All right, now let's go back to, all right, d1 is equal to d2. Give yourself more room then. d1 is equal to d2. So let's write out what d1 is. On the left-hand side, d1 is this, the cosine of s plus t minus 1 quantity squared. All right, let's keep track. All right, I'm using this one right here, and then I'm going to be saying that that's equal to this one right here. These are equivalent to each other. So plus the sine squared of s plus t. All right, and that equals the square root of, let's see, cosine s minus cosine t quantity squared plus the sine of s plus the sine of t quantity squared. Okay, so now we're done with the geometry here, and now let's just do strict algebra here to see if we can find out what does the cosine of s plus t equal according to this equation we set up. First thing I'm going to do is I'm going to square both sides. All right, if we square both sides, it would eliminate the square root. So I'll square this side and I'll square that side. That eliminates the square root then. So we have the cosine of s plus t minus 1 quantity squared plus sine squared s plus t equals the cosine of s minus cosine of t quantity squared plus the sine of s plus the sine of t quantity squared. Very algebra heavy now. We should expand now all of these. Okay, that's by foiling. So let's start doing that term by term. So let's FOIL this out. We're going to get first a cosine squared s plus t. Then we'll get minus cosine s plus t, and then another minus cosine s plus t for a total of minus 2 cosine s plus t. Then we're going to get minus 1 times minus 1, which is plus 1. So that's a FOIL right there. Okay, that was FOIL. Then we have plus sine squared s plus t. Okay, that's from the left-hand side. Now the right-hand side. We'll move down here to give ourselves a little more room. Okay, on the right-hand side, we're also going to FOIL. Cosine s minus cosine t quantity squared. That FOILed out would give us cosine squared s minus 2 cosine s cosine t. Check that by FOILing that you're going to get 2 of those. Plus the cosine squared of t. And then we FOIL the sine of s plus the sine of t quantity squared. Okay, so that would give us plus sine squared s plus 2 sine s sine t plus the sine squared of t. Okay, so we have left-hand side expanded, right-hand side expanded. Okay. Now let's try to go see what we can do to clean this up. Start noticing how we can use now some fundamental identities that are going to help to clean this up. Most specifically, I'm going to say we can use the Pythagorean identity. Okay, so recall cosine squared of, let's say, theta plus the sine squared of theta is equal to 1, as long as the arguments are the same and we're adding together the squares of these two things. Well, we have a cosine squared s plus t right here, and then look, we are adding a sine squared of s plus t, right? Those are the same as each other then. So those would combine to just equal 1. Okay? Those two terms then combine to equal 1. So the left-hand side then, we have 1, okay, minus 2 times the cosine of s plus t plus 1, right, equals. Now on the right-hand side, we have, let's see, we have a cosine squared of s and a sine squared of s, and they're being added together. So these two add together to equal 1 as well. That's a 1. Right? Then we have a minus 2 cosine s cosine t. Okay. Then we have a cosine squared of t plus sine squared of t. So those two would add together and also equal 1. Okay, because they have the same argument and we're adding them and they are squared. Right? So there's another 1. Okay, and then finally we have this term here, plus 2 sine s sine t. Okay, now let's start combining like terms. Here's the next step. We have 1 plus 1. Well, that gives us 2. So we have 2 minus 2 cosine s plus t on the left. And on the right, start combining as well. We have a 1 plus 1 over there. So 2 minus 2 cosine s cosine t plus 2 sine s sine t. Alright, now we can subtract 2 from both sides. That would cancel out this 2 right here. Okay, so that's gone. Right? So what do we have now? Negative 2 cosine s plus t is equal to negative 2 cosine s cosine t plus 2 sine s sine t. Now we spent all this time to try to prove an identity for cosine s plus t, and here we have cosine s plus t, and now we can divide by negative 2. Divide every term by negative 2, and what do we get? That the cosine of s plus t equals cosine s cosine t, and now we have 2 divided by negative 2, so this is going to become a minus, and we have the sine of s sine of t. And that's the formula we were trying to prove. So QED, we have shown what we wanted to, we have demonstrated what it was that we wanted to show. The proof is now done. Okay, so that completes it. Okay, so some heavy geometry and algebra there to get to this result. Now that we have this result, okay, we can use it in a variety of ways for numerical examples and for doing further proofs. Let's take a look at a numerical example where we might use this. Okay. Example. Find the exact value of the cosine of 7 pi over 12. Okay. That is to say, no decimals, no rounding, not even a calculator. Okay, none of that. Okay, just completely by hand. How do we figure out what this is? And we already know, okay, we already know how to use the angles in the set 0, pi over 6, pi over 4, pi over 3, and pi over 2 as references, right? Those are our known references so far. Sorry. Fix that 3. Okay. All right, so this is our set of known references. Okay, so like T bar or T hat, for instance. These are our references. And the denominators of these, none of them have a denominator of 12. Well, we can relate to these references if we can find a way to rewrite 7 pi over 12 as, let's say, a sum, okay, a sum of reference numbers or multiples of these reference numbers as well. Okay, so can we do that? Okay, well, notice 7 pi over 12, we can just play around with numbers and see if we can get it to work. You can write this as a sum in a variety of different ways. You can write it as like pi over 12 plus 6 pi over 12, right? That would equal 7 pi over 12. Okay? That simplifies as pi over 12 plus pi over 2. And pi over 2 is fine because that's in our list of reference numbers, but pi over 12 is not fine because it is not within our list of reference numbers. We want to see if we can write 7 pi over 12 as either the sum or a difference of quantities from this list or quantities which would have reference numbers in this list. By that I mean, like, if we can do 2 pi over 3 plus 3 pi over 4 or something like that, that would be sufficient as well. Because numbers like 2 pi over 3 and 3 pi over 4, we know how to evaluate the trigonometric functions already at those quantities by use of reference number and quadrant. So we'll try a different sum. 7 pi over 12 is equal to, how about 3 pi over 12 plus 4 pi over 12. So 3 pi over 12 would simplify to equal pi over 4. That's good, that's in our list. And 4 pi over 12 simplifies as pi over 3. And that's good because that's in our list as well. So we can use the pi over 4, we can use the pi over 3, right? Because they come from our list right up here. How do we use that? In this way. We want to know what is the cosine of 7 pi over 12, and we're going to be able to find it by rewriting the argument 7 pi over 12 as the sum that we've selected here. That sum is, okay, well, we might say it first, so you can follow along, the cosine of 3 pi over 12 plus 4 pi over 12, which we selected because those simplify to nice numbers that are in our list of references. So the cosine of 7 pi over 12 can be found by evaluating the cosine of pi over 4 plus pi over 3. Now, how do you evaluate that? Well, it is the cosine of a sum, the cosine of the sum of two quantities. And the cosine of a sum of two quantities by identity, which we just proved, is the cosine of s times the cosine of t minus the sine of s times the sine of t. That's the identity that we just proved. So the cosine of pi over 4 plus pi over 3, right, as an example of a cosine of a sum, would therefore be the cosine of pi over 4 times the cosine of pi over 3 minus the sine of pi over 4 times the sine of pi over 3. And now we can evaluate each of these exactly because we know what these are exactly. Recall that if we use our, definitions from the unit circle and in quadrant 1, okay, we have 0, pi over 6, pi over 4, pi over 3, and pi over 2, and we're focusing on pi over 3 and pi over 4. All right, we can recall how to evaluate these. The cosine of pi over 4, for example, is the square root of 2 over 2. No calculators needed here. The cosine of pi over 3, okay, cosine of pi over 3, that would be 1 over 2. Then minus the sine of pi over 4, well, that's root 2 over 2 again. And the sine of pi over 3, well, that's going to be root 3 over 2. Now we can do a little order of operations here, right? Multiply our fractions and combine, they will have a common denominator. When we subtract, they will have the denominator of 4. The numerator of the first one is square root of 2, and the numerator of the second one is going to be the square root of 6. And then that's it. We're done. Now, you can use the calculator to check to see the accuracy of this result here. All right, I'll let you know. Like, for example, if you go to the calculator, if you set your calculator into radian mode, all right, I'm going to say check with calculator. Make a note. This here is an exact answer. Okay, it does not simplify from there. Not to say there couldn't be other ways to write this. There could be other ways that we could write this. Like we could factor out the square root of 2. For instance, the numerator could be the square root of 2 times 1 minus root 3 or something like that. Okay, but this is an exact answer. Any type of a decimal for this would only be an approximation because this is an irrational number. Okay, these square roots up here don't simplify. But we can check with the calculator. All right, that the cosine of 7 pi over 12 is in fact equal to the square root of 2 minus the square root of 6 over 4. So I'm going to go to the calculator, and I'm using radian mode. Okay. I'll try plugging in cosine of 7 pi over 12. And I'm getting approximately negative 0.258819041. And then my calculator just runs out of room and stops listing numbers. Okay, this is not exact. This would continue. Okay, but this is as far as the calculator can take the number to. Now, if I then evaluate this expression on the calculator, all right, so I'm going to do root 2 and then subtract root 6. Okay, and then that entire quantity then gets divided by 4. And be careful how you enter that in the calculator. For instance, I'm entering a parenthesis, root 2 minus root 6 parenthesis, and then dividing by 4. If you leave out these parentheses here, the calculator is going to think you're only dividing root 6 by 4 and subtracting the result from root 2. So I'm entering it with a parenthesis there, for example. Okay, just to let you know. So this is outputting exactly the same numerical value, negative 0.258819041. Okay, so this verifies it. Yes, we do in fact have the exact value now for the cosine of 7 pi over 12. So notice this actually extends then upon the list of reference numbers that we can now refer to. We can now include pi over 12, for example, into our list of reference numbers. We can evaluate what the cosine of pi over 12 is, for example, and the sine of pi over 12 we can do as well once we have the formula for the sign of a difference, which we'll take a look at in just a moment. Now, notice also that if you have a preference for degrees, if you wanted to use degrees, you could convert the 7 pi over 12 into degrees. This is radians. How do you convert to degrees? By multiplying by 180 degrees over pi. Okay, and if we did that, well, we'll be able to cancel pi with pi. All right, we have 7 times 180 divided by 12. Okay, now 180 does divide by 12. Let's see. So they both share a factor of 12, right? So this is actually going to equal 7 times 15, right? 12 goes into 18 once with a remainder of 6, and 12 goes into 65 times. So 7 times 15, which is 70 plus 35, is 105 degrees. Okay, so the same question can be asked in degrees as this, cosine of 105 degrees. How would you do that? You could write 105 degrees, for example, as the sum of, let's say, 45 degrees plus 60 degrees. That's what we just did. It's like a pi over 4 plus pi over 3. And then you can use the addition formula. Cosine 45 degrees, cosine 60 degrees, minus the sine of 45 degrees, sine of 60 degrees. Okay, and then you would get the same answer. Root 2 minus root 6 over 4. Okay, so there's an example for how you can use the cosine addition formula to evaluate at a number, okay, by rewriting the number in the argument as a sum of either values from our list of reference numbers or a sum of multiples, okay, of numbers from there. For instance, like what if we ended up with a sum which was like, where we had 2 pi over 3, cosine of 2 pi over 3 plus pi over 4, something like that, right? So we can have a multiple of a reference number, like a 2 pi over 3, because we know how to evaluate the trigonometric functions at values like that, 2 pi over 3, by use of reference number and quadrant. So this would be cosine of 2 pi over 3, right, times the cosine of pi over 4 minus the sine of 2 pi over 3 times the sine of pi over 4. Okay, and then recall that we can say, well, 2 pi over 3, that would push us into quadrant 2. Okay, we'll be in quadrant 2 for 2 pi over 3. And the reference number for that, okay, the reference number is pi over 3. We recall that in quadrant 2, the cosine is going to be negative. It's the x-coordinate here. And the sine is going to be positive. Okay, so that's how we'll be able to evaluate. So, for instance, the cosine of 2 pi over 3, that's going to be negative the cosine of pi over 3. So this is going to be negative. All right. What is the cosine of pi over 3? Right, it is 1/2, for example. All right. And then the cosine of pi over 4, well, that's just root 2 over 2. Then we have minus. Now we have the sine of 2 pi over 3. Sine of 2 pi over 3, that's going to be positive because we're in quadrant 2 with a reference number of pi over 3. And the sine of pi over 3 is root 3 over 2. And then we have the sine of pi over 4, which is root 2 over 2. Okay, so this gives us negative root 2 minus root 6 all over 4. Another way we could write that, by the way, we could factor out the negative from the entire fraction and put it in front. Okay? Then that means if we put the negative in front of the fraction, then the numerator would be root 2 plus root 6. So now we have an entirely negative quantity here. And you can check that on the calculator. All right, you could convert these into degrees if you'd rather do that, and use degrees instead. That would be fine. What is 2 pi over 3 plus pi over 4? Okay. 2 pi over 3 plus pi over 4 with a common denominator of 12. This would be 8 pi over 12 times 4 plus 3 pi over 12 multiplied by 3, which is 11 pi over 12. Okay, so we can say that what we just found here is the cosine of 11 pi over 12. And that's equal to negative the sum root 2 plus root 6 over 4. So we just found that. What is 11 pi over 12 in degrees? All right, 11 pi over 12 times 180 degrees over pi. Cancel pi with pi. 180 divided by 12 again is 15. So we have 11 times 15 in degrees. Okay, 11 times 15 is 10 times 15 plus 1 times 15. That's 150 plus 15. So 165 degrees, in other words. So we can say we found, well, here, I'll write it here. This is the cosine of 165 degrees. And the cosine of 165 degrees, we could have written that as the cosine of, let's say, 120 degrees plus 45 degrees, okay? And we would have gotten this result. All right, so you could do exactly the same process using degrees as you could with radians. That is that you can rewrite the argument as the sum of reference numbers that we know, or the sum of multiples of reference numbers. The 120 degrees is, of course, 2 times 60 degrees. So we could think of it that way. All right, so we've played around enough with the cosine of a sum. The idea of rewriting the argument as the sum okay, is going to carry through regardless of whether this was a cosine, a sine, or a tangent formula we were using. And imagine that if we wanted to do a difference, all right, we could find, are there two numbers that come from our list of references, for example, that the difference between them, that is by subtraction, we would get an argument. Well, what would the difference formula actually look like then for the cosine? Can we figure that out? And we already have the formula here, but let's go ahead and prove that formula to be true. Okay, so number 2 right here, cosine of s minus t equals cosine s cosine t plus sine s sine t. So when this changes sine, this changes sine as well. Okay. So prove, it says the cosine of s minus t is equal to the cosine of s times the cosine of t plus the sine of s sine of t. And again, as promised, this proof is not going to be quite as lengthy or involved as the first one was. We're not going to use geometry here. Instead, we're going to use that we already know the first one, right, the cosine of a sum, and we have the fundamental identities as well, okay, including things like even and odd. Now we can rewrite the argument s minus t, okay, as a sum. We can write subtraction as a sum by choosing the second quantity to be a negative instead of a positive. S minus t is the same as s plus negative t. Well, now we have a sum, right? So we've rewritten it as a sum, and that gives us access then to the formula for the cosine of a sum, right? So we have some kind of a cosine of, if you will, a plus b happening right now. So I'm not just using the same variables, but a cosine of an a plus b, which of course would give us then a cosine a, cosine b minus sine a, sine b. That's the identity that we just proved, with just different variables, letters chosen for our variables. So we use that here. We have the cosine of the s plus negative t. The cosine of a sum, therefore, would be cosine s cosine negative t, right? Minus, because we're using the sum formula now, okay, minus the sine of s sine of negative t. Okay. So we rewrote the argument as a sum because we wanted to gain access to the identity we already proved, and the identity we proved was the sum identity. Then we just use the sum identity. Okay. We have our two arguments here. S is the first argument, and negative t is the second argument. All right. Now we can use even and odd, which are known trigonometric identities that we've already proven. We'll use even for the cosine of negative t. Okay, cosine of negative t is an even function. Cosine is an even function, that is. So we have cosine s times cosine t. An even function is such that f of negative x is f of x. Okay. And now we're going to use the fact that sine is an odd function. Okay. That's the sine of negative t is equal to negative sine of t. Okay, so we already had a negative here, and then we have the sine of s, and then because sine is odd, the sine of negative t is negative sine of t. Now our negatives will multiply together to give us a positive, so we'll have the cosine s cosine t plus sine s sine t, and that would complete the proof right there. Because we have achieved that the cosine of s minus t ends up being equal to cosine s cosine t plus sine s sine t. That completes that proof. Now where could we use it? Let's try a numerical example so I can give you one with a difference in it. Okay, we were dealing with pi over 12 a moment ago. Let's find out what the cosine of pi over 12 itself actually is. In other words, what's the cosine of, okay, in other words, that would be what is the cosine of 15 degrees. In fact, if you convert pi over 12 into degrees, you get 15 degrees. So we can add that pi over 12 to our list of reference numbers. Okay, well, pi over 12 can be written as a difference Okay, what difference? Let's see. We can do 4 pi over 12 minus 3 pi over 12. Now, other differences can be constructed, but what's convenient about this one is how each of these arguments simplify. 4 pi over 12 is pi over 3, and 3 pi over 12 is pi over 4. So we get two of our reference numbers that we're most used to. If we use degrees, we could say cosine of 15 degrees. Okay, we can write the 15 degrees as, let's say, 45 degrees minus 30 degrees. Another possibility would be we could write it as 60 degrees minus 45 degrees, for example, right? Whatever, right? There's different combinations that we could have chosen. The point is that we want to relate our new number, in this case 15 degrees, with a combination by either adding or subtracting, okay, of numbers that we already knew how to evaluate prior to this. So we can relate this new information to previous information. Now let's go back to this. Cosine of pi over 3 minus pi over 4. What is that equal to? Well, that is a difference. That's a cosine of a difference now. So we use the cosine difference formula. That would be the cosine of the first argument times the cosine of the second argument, plus the sine of the first argument times the sine of the second argument. Okay, and I'm just using the formula as stated right here. A cosine of a difference is the product of cosines plus the product of sines. And now we can evaluate. The cosine of pi over 3, okay, we know that to be 1/2. The cosine of pi over 4 is root 2 over 2. The sine of pi over 3 is root 3 over 2. And the sine of pi over 4 is root 2 over 2. Combined with a common denominator, we get root 2 plus root 6 over 4. And that you can verify on your calculator. This is an exact value. Okay? It's the same expression you would get, the same evaluation you would get if you did the cosine of 15 degrees using degrees. By either of these, you should find that you'll get exactly the same combination. Okay, this fraction might be written slightly differently, but they would all be equivalent, and you could check to see their equivalency, for instance, by checking on the calculator that they all would have the same decimal expansion. So that takes care of the cosine of a difference right there. Now, how about the sine of a sum and the sine of a difference? Okay, how could we prove those? So now I want to go for this one right here, the sine of s plus t. And I don't want to go back to the geometry. I'm going to try to relate the sine of s plus t to the cosine formulas we already had. What are some ways we can relate sines to cosines? Through known identities. Now, one way would be through Pythagorean identities. Okay, and that might relate back to the geometries we've already been looking at. But there's another way that sines and cosines directly relate to each other, and that's through these cofunction identities. Like this one right here. And this one right here, for example. All right, the cofunction identities. Now, we recall that we saw these, or we recall also that these are always true within right triangle trigonometry anyway. Right? If the angles or the arguments always add up to pi over 2 or 90 degrees, okay, by things like SOHCAHTOA. All right, the standard cofunction identities. Okay, let's prove them though a little more formally here, okay, and symbolically. Let's see, which one should we do first? Prove that cosine of pi over 2 minus u is equal to the sine of u. Let's prove that one. Okay. So, the left-hand side, we can start there. The cosine of pi over 2 minus u. All right, well, notice that that's a cosine of a difference right there. All right. So we can use the identity that we've just proved a moment ago. Right, the cosine of a difference equals the product of cosines plus the product of sines. So here we have a cosine of a difference, so we will take the product of cosines of the arguments plus the product of the sines of the arguments. And then we can evaluate whichever ones we know how to evaluate. What is the cosine of pi over 2, for instance? I like to go back to the unit circle for this. Pi over 2 is right here. Okay, and that point has coordinates 0, 1. Remember, the x-coordinate is the cosine. The cosine of pi over 2, therefore, is 0. So we have 0 times the cosine of u, plus the sine of pi over 2, well, that would be the y-coordinate here, which is 1. 1 times the sine of u. 0 times anything is 0, and 1 times anything is just itself. So this just equals the sine of u, and that proves it, and we're done. So the cosine of pi over 2 minus u is equal to the sine of u. Okay. Let's prove another cofunction identity. Okay, let's prove that the sine of pi over 2 minus u is equal to the cosine of u. Okay, recall that this comes from right triangle trigonometry, if we will. If you have, well, one of these angles can be called u, and if the other angle, let's say I call that alpha, well, of course, u plus alpha would equal 90 degrees, or pi over 2. In other words, alpha is equal to pi over 2 minus u. Right, so these angles, alpha and u, are complementary angles. Okay, so we would know that, like for instance, that the cosine of u, okay, the cosine of u, which would take the adjacent side over the hypotenuse side relative to u, is exactly the same ratio as taking the sine of alpha. Because relative to alpha, this would be an opposite side, and that would be the hypotenuse as well. Right? So this side is either adjacent or opposite, depending on which angle we're talking about. Okay, so this is this statement right here. Okay, something that we already know to be true from right triangle trigonometry. Here we are proving it formally, though, by the use of some identities here. Okay, so how are we going to do this? Okay, a little bit tricky here, because we don't have a sign of a difference formula yet. Okay, but what we do have, we have the cosine of a difference that we just found here. Okay, the sine of any argument, even if it's this as the argument, is the same as the cosine of pi over 2 minus that argument. Okay, I'm going to use that. Okay, left-hand side. The sine of pi over 2 minus u is equal to the cosine of, according to this, pi over 2 minus the argument of the sine, pi over 2 minus u. All right. So we're saying that this argument right here, let's say I call this theta, then I'm talking about the sine of theta is equal to the cosine of pi over 2 minus theta. Right? This is exactly correct. That would have to be true. That's this statement right here. Where what I'm saying is theta is pi over 2 minus u. All right. So let's continue on from here. The cosine of pi over 2 minus u, that would be the cosine of, all right, if we expand, pi over 2 minus pi over 2 plus u, but pi over 2 minus pi over 2, that equals 0. Of course, this just equals the cosine of u. So that proves it, therefore. So we have the sine of pi over 2 minus u, okay, is equal to the cosine of u. And that's what we wanted to prove. That's a bit tricky there. All right, but that proves it. Now we are ready to prove the sine of a sum formula. Prove that the sine of s plus t, okay, is the sine of s times the cosine of t plus the cosine of s times the sine of t. And let's start on the left-hand side. So the left-hand side is the sine of s plus t. Okay. And to do this, I'm going to relate this, because we don't know what this expands as yet, we have to prove it. I'm going to relate this to a cosine. Which cosine can we relate it to? Well, if the argument here is theta, we can say that the sine of theta is equal to the cosine of pi over 2 minus theta. Right? So the sine of this argument is equal to the cosine of pi over 2 minus that argument. It's the same trick that we just used a moment ago. The same technique we just used a moment ago. Now, what can we do with this? Well, this is now the cosine of a difference. Notice right here, right? The difference of pi over 2 and s plus t. We could treat it as a cosine of a difference. We can also treat it as the cosine of a sum in the following way. Let's rewrite this here, pi over 2 minus s minus t. Let's rewrite that as pi over 2 minus s as one argument minus t as the other argument. So now we've rewritten this as the cosine of a difference in this form. Why would we do such a thing? Right? Expand this now. We now have a cosine of a difference, cosine of a minus b. Right? We've already proven that the cosine of a difference is going to be the cosine, or the product of the cosines plus the product of the sines. So now we can say, well then, therefore this is the cosine of, for instance, pi over 2 minus s times the cosine of t, straight from this formula, plus the sine of pi over 2 minus s times the sine of t. And here is where we get to use, again, right? We get to use the identities that we've just proven a moment ago. We have a co-function identity here and a co-function identity here as well. Right? The cosine of pi over 2 minus s is the same as the sine of s. That was a co-function identity. Right? That was this one. The cosine of pi over 2 minus s would equal the sine of s. So this is sine of s, and we leave cosine of t alone, plus the sine of pi over 2 minus s, that's the other co-function that we did. Sine of pi over 2 minus s would equal the cosine of s. So this equals the cosine of s, and then we are left with the sine of t right here. And notice that this is exactly what we were trying to get. Sine s cosine t plus cosine s sine t. Sine s cosine t plus cosine s sine t. So we have the sine of s plus t is equal to this. That completes the proof then. Now, on your own, you can now go ahead and you can try to prove by the same strategy that I've used earlier. Okay, now you can try to show that the sine of s minus t, by use of this formula and some even and odd identities, is equal to the sine of s times the cosine of t minus the cosine of s times the sine of t. Right, that's for you to prove. All right, and you can also use this formula to do things like evaluate the sine of 105 degrees, like we did by rewriting 105 degrees as a sum, or 7 pi over 12. And you can use the sine of a difference formula to do the sine of 15 degrees, or other quantities that you can write as a difference. Okay. Now, what about if you wanted to do a tangent, though? Okay, let's finish with that. Okay. Prove the tangent identity. Okay. That is, let's take the tangent of s plus t. Okay. Let me take you back to that formula here. Tangent s plus tangent t over 1 minus tangent s tangent t. Okay, right? So this was for you to do right here, and now this is the one that I'm going to do right now. And then I'll leave this one for you to do later as well. Tangent plus tangent, okay, so the sum over 1 minus the product of the tangents. Okay, so tangent S plus tangent T over 1 minus tangent S tangent T. Prove this to be true. Let's start on the left-hand side. Normally I say start with the more complicated looking side, right? Well, you could start with that. You could start with the right-hand side. But right now the left-hand side is in fact more complicated because we have never looked at the tangent of a sum yet. So we don't know what we're looking for when we simplify this. Well, you could try it though. Absolutely. You could start with the right-hand side and you could simplify to the left-hand side. The key is to use a known identity for tangent already. That's a ratio identity. The tangent is equal to the sine over the cosine. So tangent of s plus t is equal to the sine of s plus t over the cosine of s plus t. That's the key right there. Because we already know what the sine of a sum is and the cosine of a sum as well. We've already proven that the sine of s plus t, right? So we've already proven that to be the sine of s times the cosine of t plus the cosine of s, okay, times the sine of t. And we've proven the cosine of a sum is the product of the cosines minus the product of the sines. We've proven that as well. Now we want to get this to convert into this. How do we get it to look like that? Well, we'll take a look at the form here. Notice we're going to get, on the numerator here, we have 2 terms, and we have a sum of 2 terms. And the denominator, we also have 2 terms. Okay? But there's a difference between the 2 terms. Well, we already have a sum of 2 terms here and a difference of 2 terms here. Right? So that's good. Nice, okay. How do we get them to be exactly these terms right here? Well, look for what you can do to each of the terms to get them to convert independently to each of these quantities. For instance, here's a nice thing to focus on. How do you get this to become a 1? How do you get this to turn into a 1? What's something you can do in a fraction that would turn this into a 1? You're going to have to apply it to everything. Now, let's say the thing that we can do, right, is we can divide all of these terms by the same quantity. We can divide everything by cosine s cosine t. It's like saying that we can multiply the top and the bottom of the fraction by 1 over cosine s cosine t. Like so. All right, so now if we distribute this 1 over cosine s cosine t, we distribute it to these 4 quantities here, right? We can simplify from there. This is valid to do. We can always multiply the top and bottom of a fraction by a number, okay? As long as it's not 0, we're multiplying by. All right, so we would have, what, the sine of s times the cosine of t over the cosine of s cosine of t plus the cosine of s sine of t over cosine s cosine t. All of that is over. Then we got cosine s cosine t over cosine s cosine t minus sine s sine t over cosine s cosine t. Okay, now let's do some cleanup here. We can cancel the cosine t's with each other here. We can cancel cosine s's with each other here. Here I can cancel the cosine s with cosine s and a cosine t with cosine t. And of course, when those cancel, this turns this into the number 1. Right? So here's what we have now. We have a sine s over cosine s, but that is the tangent of s, plus sine of t over cosine t, but that is the tangent of t. This simplified to a 1. We have a minus here. Now we have the sine of s over cosine of s, and that's sine of t over the cosine of t. All right, just like we had here and we had here. But now we have the product of those two. So that would be the tangent of s times the tangent of t. And this is exactly the formula that we were trying to prove, right? That's the right-hand side that we were hoping to get. So we have proven that the tangent of s plus t can be found by this formula here. Okay? So now you're able to evaluate the tangent of a sum by use of this formula. Okay? So let's say you wanted to evaluate, right, the tangent of 105 degrees, that number we've been using already. Well, you could do that by, you could write it as the tangent of, right, 60 degrees plus 45 degrees. And then you can plug into this formula. You can go tangent of 60 degrees plus the tangent of 45 degrees over 1 minus the tangent of 60 degrees times the tangent of 45 degrees equals blah, 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 and you can find out what the answer is from there. Right? But I just want to make note also, if you want, you can, sometimes I have preference for this, you can rewrite the tangent as a sine over cosine. You know, this way you don't have to memorize the tangent formula specifically. Now, you need to be able to prove a formula. If you're given an identity, prove that it's true. So this is good exercise to prove it. But if you need to actually use the identity, okay, for the tangent, for instance, you could instead use the sine and the cosine identity, right? Because then you can say, well, this is the sine of 60 plus 45 divided by the cosine of 60 plus 45, and then you can go to those identities instead. Right? And it would evaluate the same. So like the sine of 60 degrees times the cosine of 45 degrees plus the cosine of 60 degrees times the sine of 45 degrees. Okay, and then this would be over the cosine of 60 degrees times the cosine of 45 degrees minus the sine of 60 degrees, sine of 45 degrees. And the point I'm making here is that in the end, this is going to evaluate to exactly the same quantity as this was going to evaluate to. It's a matter of preference that you have for which of these formulas you'd rather use. Now, if the formulas are written down in front of you, it's maybe easier to just access this one. But if you have to memorize the formulas, if you're expected to know them, then it may just be easier to use the sine and cosine combination instead. And that's a suggestion that I have, depending on what your future is with studying this content and how you're going to get tested on it, for example. Okay? So whatever the answer is that this outputs, all right, the point I'm making is it's exactly the same as the answer is going to be for this. Okay? It comes down to a matter of preference for how you would prefer to evaluate it. And this is under the assumption you're finding an exact value, that you're not just typing into a calculator and that's it. Okay. And that you have to show your work. You have to show how you're getting your result. Okay, so that really does it for this section. I didn't evaluate these here. Okay, you can go ahead and you can evaluate it yourself, or you can let me know if you need any help with evaluating this. What I'm suggesting is, or the intention here is that when I say evaluate these, I mean put the calculator away. You know, the calculator can be used to check your answers, but you should be able to evaluate all of these expressions without the use of a calculator. So you should be able to find the exact values. And your answers in general usually will show up as irrational numbers, and you would usually want to rationalize the denominator as well. In most cases. Okay, you can check the instructions to an exercise to see if that's true. Okay, so you have a couple of different things you need to do when dealing with these formulas. One is being able to prove the formulas themselves, as they are identities, being able to prove them. Done most of that here. But for instance, you might still have to prove the sine of s minus t and the tangent of s minus t, for example. As well as other fundamental identities, right? We proved these two cofunction identities. Think about how might you prove these identities, right? Think about how you might prove them, because those could be given as exercises as well. And when I say prove them, again, I mean you're not just plugging in a number to see if it's true for the number. You have to leave the variable to be variable. It has to be allowed to vary. So you can't choose a number to plug in to make it work. And you have to show that it's true no matter what number would have been selected. And the way you do that is by relating it back to known identities and using algebraic technique, as we've discussed previously in how to prove identities. Okay. So that's one type of exercise, is being able to prove more identities based off of these identities, or proving these identities themselves. And the other type of exercise is to evaluate trigonometric functions by the use of these formulas. That can be done by rewriting an argument as a sum or as a difference, as we've done here for numbers like 105 degrees and 15 degrees, also written in radian form as like 7 pi over 12 and pi over 12. So try out the homework for that and see if you have any questions. Okay, let me or a tutor know if you need some extra help, if you have any questions with that. Okay, take care.